So we have kind of talked about this idea of outliers. We know that if something is way different than the others, that skews like our mean, our standard deviation, those types of things. So we need to know if we're going to have any of those numbers so that we know, is it better to look at the mean or the median here? Is it better to look at standard deviation or interquartile range? Sometimes it's obvious. If I said I gave a test and everybody got an A except one person got a 12%, that person would be an outlier. Can we all agree with that? They're way different than everyone else. But sometimes it's not as obvious. So there have to be clear-cut rules for what is and is not an outlier. And those are found by what are called your upper and lower fence. To find them, and this is on, everybody has their formula sheet. So it is like one of the last things on the second column of chapter 3. Lower fence is the lowest it can be without being an outlier. Upper fence is the highest. So everything between those is considered normal. If you're smaller than the lower or bigger than the upper, you're an outlier. And it's based off the interquartile range. So lower fence is the first quartile minus 1.5 times the interquartile range. Upper fence is third quartile plus 1.5 times the interquartile range. Again, we don't have to memorize any formulas. We have them all. We just have to be able to use them. So if I want to use my speed data, that second set of data we had. So remember we had yesterday in example 3, we had our 14 speeds, and then we added in the 15th car that was going 100 miles per hour, right? So to do that, we need to calculate the lower fence and the upper fence. All right. Let's go ahead and go back, just because it was yesterday. Let's enter those into our calculator. And remember, I said the second set, that's when we had the 100 along with it.
Do we put the 100 in there?
Yes. Should be 15. All right, go to your one variable statistics. Stat, calculate one variable statistics. All right, so lower fence is quartile 1. Thank you. So if I scroll down, what's my first quartile? Okay, using my formula, minus 1.5 times the interquartile range. Do you remember the interquartile range from yesterday? So what's our Q3 on this one? Yeah, 39 minus 28 is 11. We calculated that yesterday too. So if I do 28 minus 1.5 times 11, I get 11.5. So that is my lower bound. If there is a speed less than 11.5, it's an outlier. Did we have anything less than 11.5? No, so we don't have any outliers so far. Upper fence is quartile 3, which was 39, plus 1.5 times our interquartile range, which was 11. And that gives me 55.5. Did any speed bigger than that would be an outlier. Okay, so if you need a visual, 11.5, that's my lower fence. 55.5 is my upper fence. Anything here or here would be considered an outlier. So what are my outliers? Yes, sir.
Does this tag along with like percentiles? That's what we talked about yesterday?
Yeah.
Okay.
So that's an outlier because it's bigger than my upper fence. Any questions there? So I'm going to take a look at one more example here. Just because I felt like yesterday we still need a little bit more practice with some of this stuff. So I've got a couple extra ones. We don't have to do them, but I think it'd help us. So a college swimmer has a best time in the 100-meter backstroke of 45.3 seconds. The mean of all college swimmers for the 100-meter backstroke is 48.62 seconds with a standard deviation of 0.98. And then I go on to talk about his best time for the 200-meter. It's 99.32. The mean is 106.58, standard deviation of 2.38. I want to know in which race is he better. So I have to compare the two. What did we talk about finding yesterday to compare two different sets of data? The z-score. So that's R value minus the mean divided by standard deviation. So, in the 100 meter, R value, what was his time? 44.3 minus, what is the mean of the 100 meter?
48.
Divided by the standard deviation of that group. Okay. One problem I've noticed, people plugging this in, make sure, especially if you're using this graphing calculator, you have to put the top in parentheses. So if I round to a couple decimal places, I get negative 3.39. Is it good to be negative here? Yeah, what's that telling me? He's faster. Okay. Let's look at the 200 meter. So his time, 99.32 minus the mean, 6.58, divided by the standard deviation of that group, 2.38. Parentheses around the top when you plug it in. So, in which race is he better? Why? So, you have to look in the context of the problem. Like, if it were a test score, both of these would be bad, right? They're both below average. But we're talking about his time, so the faster you are, you're below average. We want the one that is most below average, so we're looking for the smallest number. Does that make sense? Do we need another one like that? You understand the z-scores? There are lots of those on your homework. Okay, last thing I wanted to do. If you go back at the end of section 3.3, I think I had an example that I was just saving to come back to. So I had like a bell curve graph, and then the next slide had these questions that we haven't done yet. Did everyone find those?
This one?
Yes. Suppose I gave a test with an average score of 84 and standard deviation of 5. Okay, if it's helpful, you can always use these curves to help you. If I said the average was 84, where does that go? And the standard deviation is 5, so what would we do?
Add and subtract.
Okay, so for our first standard deviation, 79 to 89. Second standard deviation, and third standard deviation would go from 69 to 99. Okay, you guys understand how we got those? So if I said, based on the empirical rules, so that means our data is bell-shaped, what percent of scores were between 74 and 94? So 74 to 94 is 2 standard deviations, so that would be? That's one. And do you have to memorize those percents? Nope, they're on the formula sheet. What percent of scores were lower than 79? Okay, this we might have to think about a little bit. We know 68% is in the first standard deviation, right? So each of these is 34. Okay, then, that's right. You can do 95 minus 68 is 27 divided by 2, so 13.5% in each of these. Okay, so if I did for the third one 99.7 minus 95, that's okay. And then remember, if you ever forget these, just right here, we've got our empirical rule. And then if you divide that by 2, that's when you get your 2.35. Everyone knows where I'm getting these? How would you find the last little tail?
0.03 divided by 2.
Mm-hmm. Because we had 99.7. Because 99.7 leaves 0.3%. Okay, so now we can answer our question lower than 79. So if you're less than 79, it would be these three added together. So 0.15 plus 2.35 plus 13.5 is? Okay, what percent of the scores were between 69 and 94? So 69 and 94, is that quite the third
They're
percent?
not the same.
They're not.
The last two.
Okay, so different ways of doing it. You could think it's like 3 standard deviations, but a little less. You could go through and say, okay, I'm going to have to add all of these. Any of those options would be fine.
Couldn't you just add those two, the last two, and then subtract from ours?
Yep, and subtract this one as well. 0.15
Oh.
over here. So what do we get? So this question would be really hard without the diagram. But if you just fill in your diagram, it's not so bad. What percent of scores were above 99? 0.15. Any questions there? Okay, so I'm done for today. You guys have the rest of the day to finish that homework. It's due tomorrow, and tomorrow we will start the next